Welcome back, everybody. Now it's time to roll up our sleeves and get down to work. Enough fun and games. We are very lucky to have an amazing week of mathematics and dynamical systems and ergodic theory ahead of us. There's really a fantastic program of lecturers who have agreed to share their research and expertise with us. And I'm really pleased to introduce the first speaker of the conference, Stanislav Smirnov, who does not require an introduction, from University of Genève, Skoltech, and University of St. Petersburg. He will start off this conference talking about dynamics, multifractals, and harmonic measures. Thank you very much, Stas.
Okay, thank you, Stefano. So 45 minutes I have, right?
Yes.
Okay. So it's a big pleasure to be here, and well, actually, I'm already for the second conference, so it's a double pleasure. I'm a big admirer of Marcelo, and well, it's hard to add something to all the audacious which was said, but obviously Marcelo measurates me in every possible sort of way. I can only do one-dimensional dynamics, and he do multidimensional, and he can try to organize an ICM and actually organize it, and I only can screw it up in spectacular and horrible fashion. But the only thing which sort of makes me calm that Mitac Lefleur tried to do it in 1916 in Stockholm, so I'm kind of in a good company. Yeah. So it's, of course, the thing you do for IMPA, it's really a spectacular institute, and it's people who have never done administrative job, they just cannot understand how much of energy it takes and how many theorems or just evenings with copyrights you have to sacrifice, so that I applaud, and it's really, really a nice place and only gets better with the age. Now, I tried, as I said, for a while to do dynamics, only one-dimensional at that, and the unfortunate thing is that the theorems I want to prove, I cannot prove, and the theorems I can prove, I don't want to write. It's like Michel Herman, when I was a postdoc, said that there were three reasons why he started doing dynamics, and well, one of them was that theorems were easy to prove, and another was that you would get invited to Brazil twice a year. Well, you still get invited to Brazil, but the theorems are much harder to prove. And I will speak rather about theorem from analysis I cannot prove and I want to prove. And I wasted a lot of time on it until Stefan Roy told me you shouldn't say wasted, you should say invested, because it might pay back later. And I didn't think about it for 10 years. And then my advisor, Makarov, was getting a shock prize in Stockholm. And then I gave a Laudacia, and I said something about harmonic measures. He said, well, you should finish it off. I said, well, in 3D. No, I said, no, in 2D. I said, well, I have other projects. Well, you should put them aside. So I thought about it during, the next day I went for breakfast with Carlson, and he said that I should do analytic number theory. So now who supersedes whom? I will tell about this story because it might actually have some connections to dynamics, and much of it was inspired by dynamics. So the first two slides is just what is harmonic measure and what is the relation to dynamics. So harmonic measure is one of the basic objects in electrostatics or in analysis, and in complex analysis even more so. So, well, here are four possible definitions. So suppose you have a domain, in this case it's interior of a von Koch snowflake, and you can do these four things with it. You can start Brownian motion at some point and look where it hits the boundary. So this approach, which was implicit in Courant, Friedrichs, and Levy, paper on numerical analysis, and then Kokutani formalized it, Shizuo Kokutani. Then you can map by conformal map to a disk and take the measure on the disk and pull it back. And it's the same as the heating measure on the boundary, because Brownian motion is conformally invariant, and on the disk, if you map point to the center, obviously the measure is rotationally invariant, so it's the length. But you always can do potential theory, so it's electrostatics. Electrostatics in the plane has kernel not 1 over r, but logarithm of r, so you take measure which minimizes the potential. So here I've written it with the other point at infinity. So we should think that there is another point where you have +1 charge, and you put -1 charge on the boundary of your domain, and you make it out of cast iron, and then it will distribute in the most efficient way. And there is interaction of boundary with this other charge, and then there is in itself, and so you minimize this functional. Then it's the unique measure which solves Dirichlet problem for Laplacian. For example, if you have a temperature in the room which is stationary, and you want to calculate it knowing temperature on the boundary, then harmonic measure tells you from this point how to calculate it. So the best relation in dynamics, if we study it in outside, so I will switch to outside of the domain, and I'll switch to reference point being at infinity. So it's just exactly the same thing. So this is the same formulas I've written before. And here there is a hyper nice connection to complex dynamics. So suppose that, so we study it in the domain at infinity, so it's on outside of some compact set. So suppose this compact set is a polynomial Julia set. So we pull our favorite rabbit from the hat. And then we have this map phi, and so it's a Julia set for some polynomial, in this case it's quadratic one. And we know that Riemann uniformization map, it conjugates dynamic z to the power d to polynomial dynamics on the Julia set. It works in the outside. If the Julia set is nice, say, locally connected, say, hyperbolic, you can continue it up to the boundary. It doesn't work inside the components. If you want to do inside components, again, you find periodic component, you conjugate, but you get nice relation to harmonic measure, only if it there conjugates to goes to z to the power d. If you have, if you have some other things, you get different picture. Now, this was probably first noticed by Leonard Carlson. He gave it to one of his first grad students, Brolin, who went later into teaching as a thesis problem, and he sort of noticed that if you take preimages of a given point, they would distribute it themselves according to harmonic measure, because that's clear on a circle. If you take angle doubling on a circle, you take preimages, and they would just be fractions. And then Misha Lubitsch proved that it's a measure of maximal entropy for any Julia sets, not necessarily a hyperbolic one, so it's a non-trivial and important theorem. And then you can study how well preimages converge to omega. Then, of course, you need some hyperbolicity to know that, but that's the connection. Now, I had the word multifractals there, and we all love fractals, but somehow, multifractals are maybe, apart from a couple of areas of math physics and dynamic systems, they are less well known, though they play a very important role. And multifractals are sets where you have different fractal behavior for different Gibbs measures, but basically every fractal will have that. But to have this multifractality, you need to have two reference measures and kind of build a bridge between them. So let's look at harmonic measure, and the other measure being the just Euclidean Hausdorff measures, their family. And let's look how harmonic measure looks on a polygon at a corner. So if it is conformally invariant, if I have a corner of pi over alpha, then map z to the power alpha opens it up and gets to a straight line. On a straight line, locally harmonic measure is just length. It's what we see for the circle. So there, harmonic measure of both some radius is just its radius, and radius r was mapped to r to the power alpha. So we see at the corner of a polygon, harmonic measure will be r to the power alpha, where alpha is not the angle is pi over alpha. And the angle is between 0 and infinity, so alpha is between 1/2 and infinity. And so you get some power law behavior with power between 1/2 and infinity. And since radius is small, then 1/2 is the biggest power, so delta to the power 1/2 is much bigger than delta squared to delta cube. Now, it is a theorem which is usually referred to as Berling estimate. It was first proved by Karleman, then by Alfors, then by Berling, but Berling applied it to more effect than Karleman and Alfors, and then Carlson yet to more effect. And Carlson was a student of Berling, so that's why it's called Berling's estimate. And it's a very nice one, and it says that for any dimensional polygon with an absolute constant, you take no more than square root of r. Now, there is a much more difficult theorem, which is proved by Makarov, my advisor, that harmonic measure has Borel support of dimension 1. Now, look, what we have on the right, we have a von Koch snowflake, only a square one. And we have graphical representations of two harmonic measures, from the outside and from the inside. So I made this picture because later I'm going to compare them. And if you think that if that were a polynomial Julia says, then these blue lines would be preimages of some lines, so the frequency of them that tells how dense is the harmonic measure. And you see that there are spikes where there is a more harmonic measure. It's where the angle is bigger. And that's actually because it's electrostatics. That's why we put this metal rod so that the lightning strikes them, because lightning strikes where, according to harmonic measure, so it strikes where the harmonic measure is bigger. So if you put a lightning rod, that it strikes at the lightning rod. On the other hand, there are fjords where it is smaller. But obviously, you cannot put many rods, because if once you put one rod and then you put second nearby, it starts screening the first one. But you can have many fjords. So there is this already multifractality. Then you can have more fjords than rods, but in rods the measure is higher. And the Makarov's theorem says that apparently for the harmonic measure, the importance are places which are flat, even in this snowflake. That the spikes, they have high harmonic measure, but there are few of them. Fjords, there are a lot of them, but they have small harmonic measure, and it all lives on a Borel set of dimension 1. Look, the compact support, it's difficult to say. It's one of very few theorems I know that physicists didn't believe when they heard about. They thought that there can't be theorem like that. So basically, a compact support of harmonic measure has the same dimension as this counter set, so it might have dimension 2 even. But there is a Borel subset, which is everywhere dense, where it lives, where 100% of it lives, and it has Hausdorff dimension 1. Or even better, it has sort of sigma finite length. OK, but then you can study, it means that you leave out with this theory many things, so you can study fractal spectrum, and that's the easiest definition. You take the set of points where it scales like some power alpha, and you denote the dimension of these points by f of alpha. Now, you can write definition, but if you write definition, it will have suprema and infima, 3 of them, and then even when you first see them, it confuses mathematicians, like in calculus, definition of continuity confuses the first-year student. So it's, but informally it's like that, and you should understand that if you have a nice set, like a von Koch snowflake or a Julia set of a polynomial, that works as a definition. Because there will be a Gibbs measure where you have exactly this behavior, so it's, if you're a dynamics person, it works as a definition, and then you can show that it's related to others. And well, that's the multifractal spectrum, and like 2 estimates we know. Berling estimate can be reformulated that it starts at point 1/2, this sort of concave curve. It's actually not easy to see from this definition, but there are some reformulations where I easily see that it will be a concave curve, and we'll come to that later. And Makarov's theorem says that f of 1 is 1, the dimension of points where omega is comparable to R is equal to 1. So this is true for simply connected domains. For counter sets, it actually might be smaller. Now, what we want to do next, we want to relate it to dynamics. And there is a definition which is more popular in dynamics on this. It's called sometimes pressure. For measure, it's called packing spectrum. And the definition here, it's a bit scary because it has all the limits and supremums in it. So what I say that I take lim sup over all packings. Packings, it's a cover by non-intersecting bows. Well, not necessarily cover, just slow some non-intersecting bows. And they have small radii, and the radii tends to 0. And then you take this sum, and if you look at this sum, so you fix t. So it's t where we want to evaluate our spectrum pi. And we put omega to the power s. Since omega is small, the bigger the power s, the smaller is this sum. And we take supreme s so that the sum is finite, or smaller than 1. And this is the definition. So from this definition, if you are bored, it's an exercise to see that you have a convex function. It's, well, there is an area popularized by David Ruel, which is called thermodynamic formalism, where you prove that for various kinds of sets or measures, there are various nice properties of this pi. So for example, one nice property, then you could strict yourselves to packings where all omegas have the same, or all the bows have the same omega, all the bows have the same radius. And this kind of comparing two measures, because if you have this conformal map, so I made a picture of a small part of it, then there are radii on the right in my von Koch snowflake, and on the left in the disk, the radii are just harmonic measures. And you can, if you have, this will be important for the later, if you have some arbitrary domain and you approximated spectrum very well by some particular packing, then you can play von Koch snowflake with this packing. So you have this packing with, say, 4 bows, and then you make a copy of these 4 bows inside of each, and you do iterate, and you get von Koch snowflake, and it turns out after some very complicated work that it will actually have the spectrum, dynamical spectrum given by that. So this spectrum is like this graph on below, so it goes like that. And if you've done dynamics, you've seen it as a pressure for dynamical systems, and there are several people in the room who wrote papers about that for various dynamical systems. So what we know in dynamics, so this is, for example, that was done in Ruel's book for some self-similar systems, that is these 2 things, f and pi, they're related to each other by what's called Legendre transform. So basically you take, for example, there for pi you take, for pi you take tangent line, and the tangent line, if it intersects here at f of alpha, then it intersects here at f of alpha over alpha. So that's the way to get f of alpha from pi, and there is a similar in the opposite. And what Makarov proved is what I said on the previous slide. So the idea is straightforward, that you take some domain, you approximate its spectrum by some small enough packing, and then you iterate it to get von Koch snowflake. And you get von Koch snowflake where spectrum is close. So it sounds simple, but unfortunately you have this Kirby distortion which accumulates with every step, and you have to get rid of it. So it's a difficult theorem, but basically theorem says that no matter which domain I give you, there is a snowflake which has arbitrarily closed spectrum. And for snowflake, you have these many nice properties. For example, you can get rid of all this lim sup in the definition. You could just take the dimension of this set, and then you have this fractal formalism. Now I want to do the very same thing for the dynamics case. And for the Julia set, so now, again, I feel a bit uneasy because there are some people who know that better than I do in the room. And on the other hand, if you see these formulas for the first time, they look a bit intimidating. So you have some polynomial, f. Then what you can do, you can define the pressure by taking all the preimages of order n of some point z. You should take non-exceptional points so that it really has preimages. So the best thing, if you have polynomial Julia set, just take something outside close to it. Then preimages, they accumulate to it. As we know, they distribute themselves by harmonic measure. But you sum the derivative from these preimages to this point to the power t, or rather minus t. And if you take a point and you take its preimage, what you can do, you can take a bow at this point. And unless you had critical point, the preimage of the bow will have the radius approximately given by these derivatives. So it's equivalent to nice situations that you have a packing of the bow and you sum their radii to the power t. And the packing gets more and more because you get more and more preimages. So if it's hyperbolic, it's not very difficult to do. And you get the same pressure. So you have here logarithm base d because one point has d preimages. And the nice observation which was due to Bow and Ruel and came from other parts of dynamics, that you can study this number as an eigenvalue of the transfer operator. So there are 2 conjugate operators. I don't want to discuss in which spaces they act. Just the first one acts on some function space. The second acts on the measure space. And the one with the measure space, what it does, it pulls back the measure and multiplies it by the Jacobian to the power t. The second one, it pushes it in the other direction. So there are several preimages. So for a point, there are several preimages, and you combine all of them and multiply by derivative. So these are appropriate space. You can sort of informally see that it's the same thing to study this spectral radius. And logarithm of it is p. And our spectrum. And then there were several nice observations. So Bowen observed, and it's related to SRB measures and Patterson-Sullivan measures. Julia says they called conformal measures, that the root of this pressure is exactly the dimension of the Julia set in nice cases. And the root is where p is 0, when logarithm of lambda is equal to 0, so lambda is equal to 1. So it's where eigenvalues of these operators are equal to 1. So now if you look at the second operator, suppose that there is eigenvalue 1 and there is a measure which is eigenmeasure. Then its measure, when you map it by f, it exactly scales like f prime to the power t. And it's, for hyperbolic case, it's already, today, well, it's was more difficult back in the days of Bowen, but today it's sort of clear that the measure will have to be Hausdorff measure with the exponent t. So it means that it lives on your Julia set. It means that the dimension is t. And another nice observation that if you have this eigenfunction and eigenmeasure, and you multiply them, then you get an invariant Gibbs measure. And that's for every value of t. So it means that on this whole line of spectrum, at every point, there is a Gibbs measure which does something different. Now, that was used in a paper of Roelle, which answered at the time a question of Sullivan. So Sullivan asked whether the dimension of Julia set depends analytically when you change the polynomial. And the answer was yes for hyperbolic polynomials. And the way Roelle did it, he proved that this transfer operator is in some sense compact. Well, actually, that's the only time I've seen people use the PhD thesis of Grothendieck about nuclear operators. But also, I have never seen people who understand PhD thesis of Grothendieck. So it's so Roelle in his proof uses the following fact that the limit of real analytic functions is real analytic, which Weierstrass told us is not true. So, the proof, the details of the proofs are not correct, but you can easily fix it by going into, well, not easily, but you can fix it. But the idea is the same. There are several approaches how you prove that this separator is compact. Like there are like Carvangel-Leviran does these Banach space cons. You can do the compactness in some Sobolev spaces, which are like you can do nuclear operators of Grothendieck, but then you should understand Grothendieck. So there are many approaches. But then if you have an isolated eigenvalue for compact operator, which changes analytically in T and analytically in F, then by implicit function theorem, it analytically changes, so dimension changes analytically. So you obviously don't have it for arbitrary polynomial for the full spectrum because, because dimension of Julia set is not an analytic function of F. There are Julia sets of dimension 2, it just wouldn't be possible because the dimension of Julia set is bounded, and if you would have some relation to complex analyticity, but even real analyticity is not possible. But there are some things. So, for example, this is sort of important for what we'll do later. For negative T, the spectrum for any Julia set is analytic, except there might be some phase transition if the Gibbs measure gets atomic. But that can be precisely described. So this is exactly the same function as before, only defined dynamically. And also there is a nice dynamical thing, which is called variational principle. So I said that to every point corresponds a Gibbs measure. So this spectrum is a supremum of a functional over O invariant mu, which is entropy of a measure minus T Lyapunov exponent of the measure. And the nice thing about this functional is that if you have entropy of a measure, you don't care about the Julia set. For example, if you have two Julia sets which are conjugated, you can calculate entropy on one of them, so F is not important. So if you only Lyapunov exponent is important, so when you change, it's enough to look only at Lyapunov exponent, so that allows to do nicely some things. And Manning observed that this approach gives Makarov's theorem the dimension of harmonic measure equal 1 for Julia sets very easily. Unfortunately for him, he observed it like half a year later than Makarov proved it in general case, so it didn't have a big bang, this theorem at the time, but it's really a one-line approach, and you can just write this definition, and you know that harmonic measure is measure of maximal entropy, so thanks to Misha, so you plug in this log of d base d, which is 1, so the first term is 1, and the second term is integral of log f prime with respect to harmonic measure, and log f prime is a harmonic function, so its integral over harmonic measure, its value, it's infinity, and its value at infinity is 0, so you get 1 minus 0, hence 1. I told you the complete proof. It's really easy. Okay. Now I come to the theorems which I want to prove. What we want to deduce is not the behavior of this for individual von Koch snowflake. We want to get maximum over all von Koch snowflakes or all sets. So basically, we define this object, which was defined by Makarov. We take supremum of F over all domains, or supremum of pi over all domains. And then there is a conjecture which took 5 people to make, Brennan, Carlson, Jones, Kretzer, and Makarov, that the maximal value has this nice formula. Now, the unfortunate thing is that we have no intuition why it should be that. So they just made, it's kind of, like my friend Benoit Mandelbrot, he made, we know lots of successful conjectures, but he made so many conjectures that like 10% of them were successful. So for example, he conjectured the Mandelbrot set is disconnected. Maybe because the printer was bad and didn't print some lines. But on the other hand, he conjectured it has dimension 2, and that's sort of a great conjecture, which eventually was proved. Or he conjectured the boundary of Brownian motion has dimension 4/3, which is even harder to observe, and it was proved. Okay, so here it's a bit wild, like some Mandelbrot's conjecture, and essentially it's the nicest formulas and the only nice formula which satisfy everything we know. I won't make a list of what we know about these things, and if they hold, then there are many nice corollaries. Now, what I really said is that there are only some numerical evidence and no real intuition and only weak estimates. So what we know, there is a fractal approximation theorem by Makarov that it's attained since every domain can be approximated both snowflakes, the maximal also can be approximated by snowflakes. So for maximal, there is this Legendre transform relation between two spectra. So if one of them is 2 minus 1 over alpha, the other is this quadratic function. Then there is a Falkrohr theorem, which has never been really written, that it's attained for Julia sets, it's attained for quasi-Fuchsian groups. So it's, we basically wrote it in a paper with Belay for Julia sets when we were determining Littlewood constant, and then Peter Jones and Binder saw that they already have this written, so we decided not to write it, and that 25 years have passed, they haven't published it yet. But it's sort of people understand how to do this, so if it's needed one day, people will write. And the only thing we know is a theorem with Nick Makarov and Leah Binder is that the supremum is attained for simply connected sets, and it actually uses unwritten results of Binder and Jones that you approximate by Julia sets. And then you vary Julia sets in the sort of outside components of multidimensional Mandelbrot set, and the maximum will be attained on the boundary where you get connected things. So it's one example where a connection to Julia set, which is not proven in writing, is used. Now, why is it important? So I'll just quote here 3 papers by Jones Makarov, Carlson Makarov, and Vilayev and myself. So one thing is Carlson Makarov that if you look to pi at -2, this conjecture says that it should be 4, and this is equivalent to Brennan's conjecture. So Brennan's conjecture says that any map on a disk has derivative integrable to the power 4 minus. So clearly, if you take derivative to the power 2, it's just the ratio of areas, so it's integrable. But then if you check the maximal angle by Berling theorem is 360 degrees. If we angle 360 degrees, the derivative will be the maximal. It will be 1 over square root of z. And 1 over square root of z to the power 4 is 1 over z squared, which is integrable in the plane. Well, almost. It's like Landau said that chicken is not a bird, logarithm is not infinity. So it's almost integrable. But as I said, when you add spikes, they start screening each other, but we have to prove it. So we don't know whether 4 is maximal power. It's equivalent to pi minus 2. And pi of 1 gives optimal coefficient decay rate for bounded conformal map. For unbounded, it was settled by Bieberbach. For bounded, it's still wide open. And max growth rates for the length of Green's lines for these snowflakes, and Littlewood's constant in value distribution theory. And just an example, what is the best theorem known for pi of 1? It's conjecturally 0.25. We know that it's bigger than 0.239 something. It's more than 0.462 something. So it's still quite a gap. So it would be nice to determine it. I tried for a very long time, and now I'm trying again since this summer. And I think at least I have some numerological ideas why it should be exactly this. I will just end with 3 questions. But before this, all these ideas, they take root in a work of Kari Astow and myself, which was motivated by complex dynamics. So I'll start with this. So because, well, every talk should have one proof. So I will prove one thing. And then I will remind what is a quasi-conformal map. Quasi-conformal map, which is a map which sends small circles to ellipses with bounded eccentricity. And it can be defined by its Beltrami coefficient mu, which is d bar over d. The conformal map has d bar 0, and quasi-conformal has d bar bounded by d times some k, and k is smaller than 1. And there is a measurable Riemann theorem by Alforsbirs and Bayarsky, which says that if you have Beltrami coefficient, then there is a unique phi up to uniformization, and depends analytically on mu. It has been, since Sullivan, it has been really successful and spectacularly used in complex dynamics. Sullivan used quasi-conformal deformation to show that there are no wandering domains. Then there were these Hermann rings constructed by Hermann, and Shishikura uses it, so everyone uses it. It's kind of a moveton not to use it in complex dynamics. And then there was a spectacular theorem of Kare-Astava, which was inspired by dynamics. And he proved that if you have a K quasi-conformal phi, then it distorts dimension by no more than something. And here's the estimate, which looks a bit ugly, but the result is sharp. It's easy from the proof. It's attained for square counter sets. And if dimension of E is equal to 1, then this simplifies the dimension of phi of E is at most 1 plus K, at least 1 minus K. So if K pushes to 1, you can put it down to 0 or push it up to 2. Now, if you have a quasi-circle image of real line, then its dimension can never go below 1. So it's sort of indication in the proof that it also can't go very high either. And then Becker and Pomerenke proved actually before Astava that it's no more than 1 plus 37k squared, and Astava conjectured that it's no more than 1 plus k squared because it's a nice thing. It's the same as these conjectures of Mandelbrot or Carlson Jones and the others. And surprise, the conjecture was correct. But then there is another bad surprise that we thought for 10 years that it is sharp, and then Oleg Ivory spoiled all my crystal dreams, smashed them on the floor saying that it's not sharp, and it's, well, in a beautiful sort of way with Weyl-Peterson metric. So we know that the dimension of a K quasi-circle is at most 1 plus K squared. Unfortunately, it's not sharp. There is a better estimate we don't know. And there is a Doe statement, which I will use, that if you have a quasi-conformal map which preserves the line, and you have set of dimension 1, its dimension never drops below 1 minus k squared. But again, there should be a better estimate. Well, but ask Oleg, he should write a nice formula, and he hasn't so far. OK, so I will do that's the only proof I'm going to give. I will do the proof of this thing. And one uses a very nice idea, which was very successful in dynamics. So, well, there is actually, yeah, IMPA connection. So it started by Ricardo Manier and co-authors, Manier, Sad, and Sullivan, and then there was Sullivan first, and Bersroyd and Slatkovsky, that if you have homomorphic motion of a set, then you can always prolong it to homomorphic motion of the plane. And homomorphic motion of the plane, it works, it will give you these quasi-conformal maps where Beltrami coefficient changes homomorphically. And the easiest way to do it, you take some Beltrami coefficient, so it's a field of ellipses, and quasi-conformal map changes this ellipsis into a circle. But then you multiply this field of ellipses by lambda. So lambda rotates them and stretches. And then you get a new quasi-conformal map, and apparently the dependency will be analytical. So what you do, you take your set, for which you want to prove estimate. It's on the, so I will do it on the real line. And then you approximate it by von Koch snowflake, by some counter set. And you change Beltrami coefficient. So for lambda in a unit disk, you get coefficient mu lambda, which is just lambda times mu. You get map phi lambda. So you have this packing of disks, which involves in the motion. So the disks have complex radii r lambda, and you have these counter sets you get from the disk by iterating. So why do you do this self-similar thing? You don't really need to do it in the proof, but it's more beautiful with this because you have this exact formulas, no lim sup, no nothing. Now, there is this pressure, and as I said, you can write it as just sum of rj to the power t. And then here we have variational principle, but here it's nicer because you have a counter set. So invariant measure is just some Bernoulli measure. So you take counter set with, like, on my picture, it was with 4 disks. So any invariant measure will be given by 4 numbers, how much, which is relevant for this, how much goes to the first, second, and so on. So you have these numbers P1, P2, P3, P4. And then the entropy of this measure is sum of P log 1 over P. Lyapunov exponent is sum of P log 1 over R. And the variational principle just follows from the Jensen's inequality. So the pressure of which dimension is a root. The pressure is supremum of entropy minus T times Lyapunov exponent. Now, entropy doesn't depend on lambda. When I vary my set, entropy of measure is the same. Only Lyapunov exponent depends. And Lyapunov exponent is harmonic in lambda because it's sum of logarithm of Rj. Rj changes analytically, logarithm of Rj changes harmonically. So instead of some complicated dependence which we don't know, we know it's real analytic, we get a harmonic dependence in parameter for one blue thing. But then our thing is supremum of blue things. So our thing is a supremum of harmonic functions, so it's subharmonic function. And then for it we can apply Harnack's inequality. So Harnack's inequality, at the center we have something on the line, so dimension is equal to 1. Dimension is equal to 1. If we write through variational principle, we get I over lambda is no more than 1. Then lambda minus I over 2 is at least I over 2. But also dimension is always no bigger than 2. Because we're in the plane, these disks, they move, they cannot intersect. They don't overlap. Yeah, there are some setups where they overlap, then the dimension can go above 2. And some of the people I see worked on it. But here they don't overlap. So dimension is no more than 2. So again, we have estimates of the spectrum. Lambda minus I over 2 is at least 0. And you see that you have two functions with two estimates in the top. And one estimate says that some function which is harmonic of lambda is positive. And the other says that the center is at least I over 2. Then there is a Harnack estimate. So if you have positive harmonic function over the center, you know that it's at least something. And if you write it down, you get exactly the estimate 1 plus absolute value lambda, 1 plus k estimate of S tower. Now, if we want to do it in my case, what we do, we find an antisymmetric motion where this blue thing is symmetric. It's an even function. And if you have an even function, then Harnack is twice better. Instead of 1 plus k, you get 1 plus k squared. Well, you can just map to usual Harnack by taking square root. And this is a nice thing, so I will just show you the theorem because it's important for my questions. So it turns out that for any quasi-conformal map to a quasi-circle, there is an optimal version to choose Beltrami, and you get it from antisymmetric Beltrami. So what is symmetric Beltrami? Symmetric Beltrami is when on two sides of the line, two ellipses are mirror images of each other. And then by symmetry, line is mapped to the line. When they are not mirror images, but at 90 degrees to mirror image, that's the antisymmetric. So it turns out, of course, when I wrote this paper, it turned out sometime later that 30 years ago, Remert already had this. But it's how mathematics goes. I bet Poincaré had it before Remert. And, well, someone had before Poincaré. But here there is this nice thing which tells you always can describe any quasi-circle by an antisymmetric thing with beta Beltrami or any map of line to itself by symmetric with beta. So this is the proof. Now I come to the things which I cannot do, and I'm trying to do intermittently with some gaps of 10 years sometimes. And how to estimate universal spectra and how dynamics might help. Of course, the first thing when this appeared, we thought, and that was the reason why we're doing spectrum with Makar for Julia sets, is that for Julia sets, there are some nice estimates because they are Julia sets. And Brennan conjecture, for example, Sasha Wolberg, he wrote this Krzysztof Baranski paper where they prove it for quadratic Julia sets. But it's just some estimate of multipliers for quadratic Julia sets. And unfortunately, if they would have done it for any polynomial of any degree, that would have worked. But we don't have fractal approximation by quadratic polynomials. Actually, it's not an important but it's curious question, since most of the things you see inside the Mandelbrot set, does Mandelbrot set have a maximal spectrum? Mandelbrot thinks thought it does. OK, so there are three things I will discuss. And, well, let's just start with the first one. So we have this theorem that if you have measure nu on a real line, its dimension is 1, and we map it by k quasi-conformal thing so that it's still in the line, its dimension is at least 1 minus k squared. Now, theorem, assume that this estimate is sharp. Sharp in the following sense, that if I give you measure of 1 minus k squared dimension, then I can move it to dimension 1 by KQC map. Already it's not sharp, because I had this crystal, well, it's not sharp because, for example, if you have a Cantor type measure with gaps, no matter how you move it quasi-conformally, gaps will still remain, so we never move it to 1, but we don't need it for Cantor measures. We need it only for Gibbs measures, important for Julia sets, and they are never Cantor. So, but then, of course, Oleg came and with his beautiful paper ruined my crystal dream, so we know that it's not sharp, but the whole method works even if some other thing is sharp, so I'm just describing the method. So in this particular case, if it's sharp with this thing, then we can prove this conjecture about universal spectrum. And this is numerological coincidence that if this is sharp, then the other thing is also sharp. Unfortunately, since this is not sharp, there is no this connection, but this not sharp doesn't imply the other not sharp. So it's despite I like trying, but okay. So how does it do? How do we do this thing? We do this thing in a very interesting way. We take this blue line, which gives a measure. So we have this measure sigma, which has dimension 1 minus k squared. And we move it by homomorphic motion to measure dx. Now, measure dx is a linear measure. So if you map it conformally by Makarov's theorem, it has dimension 1. This map, there is this rather crazy thing. I write map phi as phi times psi k, which is this thing, times phi inverse times psi k inverse. So it's all cancels out. Let me check. Yeah, these two cancel out, these two cancel out, so only phi remains. So what you get is that one of these two things is conformal on one side. It moves the thing of dimension 1. So by Makarov's theorem, it gets it to dimension 1 because it's a conformal image of a thing, so it's a harmonic. And the other thing is a conjugation of it's a conjugation of k quasi-conformal map. It's a k quasi-conformal map. And by Astauer, it's no longer in the line, but still by Astauer, we get estimate no more than 1 plus k. So what we get is from this funny, I never, I'm not algebraic topologist. I don't write such things normally. But we get estimate that here we have 1 plus k, and here we have 1 plus k squared. And then we draw a line through 1 plus k squared and 1 plus k, and draw these lines for OK. And surprise, surprise, this is envelope exactly of this predicted thing. Now, this is a good numerological thing. It's not as good since the smart guy lack ability to be true in it, but whatever estimate we get there, we'll get some estimate here. So here is basically a question. And it should have some dynamical meaning. It's sort of related to these questions of prolonging quasi-symmetric maps as quasi-conformal, which Cliff Earle and Adrien Douady worked on. So some sort of dynamical thing. I have a nice Gibbs measure on a line. How the best way, most efficient, move it to the length? And this measure, it comes from some Julia set, so it should be some sort of dynamical way to do it. Well, if you want, we can discuss it at longer time, just here or come to Geneva. And I believe that there should be some sort of dynamical thing there. Now, the second approach is two-sided spectrum. So you can incorporate in this spectrum also a spiraling. So suppose the thing is spiraling at speed gamma and logarithmic spiral, and then you have f of alpha gamma. And then you can compare harmonic measure on two sides. So power alpha minus on one side, power alpha plus on another side. Spiraling gamma, spiraling is the same speed on both sides. Then, for example, Berling estimate in this case, it looks like that. 1 over alpha plus 1 over alpha from the other side is 2 over 1 plus gamma squared. So I don't want to go into all details. There are also scary slides I have here with these formulas. But I did the same mistake as last week. I realized today in the morning that I have slides for 1 hour and a half. And yesterday I thought that they are not enough for 45 minutes. We do the same thing as we did for Julia sets. So we change the Beltrami coefficients, but now we have two parameters. We have Beltrami coefficient, which is symmetric, and multiply by lambda from unit disk on one side, and eta from the unit disk on the other. And then it turns out that there are some very nice formulas, very nice numerology. Now parameter is not a disk, so the usual one for Julia set would be you parameterize Fatou component of Mandelbrot set by a disk. You change this Beltrami, it's all like Manet Sullivan, and you parameterize by disk. But now we have two sides, and I don't know what it corresponds to. Probably the better language is quasi-Fuchsian group, not the Julia sets. But again, you have some dynamical quasi-circle. You take Beltrami, which is symmetric, so in the beginning it's a circle, but then you change it differently on two sides. And then there are beautiful formulas, so I don't want to just this 25th frame. So you define this function phi capital, which is 1 minus entropy over lambda. It works better than the spectrum. And you rewrite the usual statements that dimension of a set is no more than 2, that on the line we have a set which is on the line, on the diagonal, dimension is no more than 1, and we have some symmetry when two sides flip around. But in the end, I'll just show the last slide. Let me see, what is the last slide? So we have a pressure-related quantity phi, which is a function from by disk squared, to a disk. We know that on the diagonal here is lambda, lambda prime. It is positive and subharmonic. Actually, the function is analytic in lambda, anti-analytic in lambda in the second thing. And then we have this crazy symmetry and many more things. The big conjecture is equivalent to this determinant being positive. Well, it looks beautiful, so it's a reason that the conjecture is correct. But basically, there's a question, have you any time seen harmonic type things in by disk? Well, that's maybe not appropriate conference to ask this question, but some people do multidimensional complex dynamics. But or have you really seen some setup where you really were a quasi-Fuchsian group? And the last one is the same thing, but what you do, you have these two disks. You can look at it as a welding, which gives you a quasi-circle, and the welding is given again by two Beltrami coefficients. What you do, you get, well, this picture. And you can define three measures. You take original measure dx. It gives you some measure on upper circle, some measure on lower circle, some measure when you glue them in a bed. So there are three dimensions, d plus, d minus, and d. It turns out that the conjecture before equivalent by this to this beautiful thing. 1 minus d squared is no more than 1 minus d plus times 1 over d minus. And if d minus is equal to 1, you have 1 minus d squared no more than 0. It follows from Makarov's theorem. So again, how to interpolate? So this is a question, can we interpolate? Do we have some nice dynamics for weldings also, which are called matings in dynamical community? And the other thing is that for quasi-circles in the quasi-Fuchsian group state, the left-hand side is exactly 1 minus lambda 0, where it's the best eigenvalue for this manifold. And this is very tempting to put instead. For example, just prove 1 minus lambda 0 no more than 1 minus d minus times 1 over, well, already that would be a big thing. But I don't know because when I plug it in, well, my talk is up. I don't know because if I plug it in, I actually end up walking the same trail I came to this point, but in reverse. Okay, so I need some help with dynamical measure on a line, quasi-conformally deforming it to lengths, or making dynamical system of some motion where you move some dynamical curve on Beltrami on two sides, or welding, not welding. I'm not welding conformal structure, I'm welding it. Well, okay, but then I will weld it. Well, I think that's it.
Thank you very much, Stas. Are there any questions or comments from the audience?
Well, so Misha asked what's the role of antisymmetric Beltrami differential. Look, so there was this beautiful theorem by Astava. It's one of the, well, it's like your paper that harmonic measure of maximal entropy. It's sort of nice and cute, and you see the proof, and there is a beautiful idea that the distortion is the dimension of a KQC image of one-dimensional set is no more than 1 plus k. And when I was doing this for quasi-circle, I needed somehow to use that it is a quasi-circle. And obviously, when you have a symmetric Beltrami, then the line is sent to a line because the picture is symmetric. So if Beltrami is symmetric with respect to mirror. And that is kind of indication that if it's opposite to symmetric, that if these two ellipses, so the upper one, not the image of the lower one, but the opposite. And the opposite would be this rotated by 90 degrees. So you don't stretch in this direction, but you shrink in this direction. And then sort of I found that, well, any quasi-circle has a parameterization which does this, where k is even better. And of course, it's the line is mapped differently on quasi-circles. So you change these underlying Gibbs measures, but the resulting compact set is the same. And that allowed to prove this Astava's conjecture. Now, when I saw that there is this numerological coincidence, I was sure that actually this conjecture is true until the day Oleg Ivry came with his hammer and broke the whole thing down with his nice proof. But if it were true, if it were sharp, and there would be an extremal quasi-circle, it would be a holomorphic motion which goes like that. So there is a holomorphic motion of a curve with some dynamical structure on a disk. Actually, I have a picture, but it kind of, I didn't want to show it, so it went a little bit sour. So let me show it. So you see the square stands for the letter phi. So it would be a holomorphic motion which is symmetric on a blue line, antisymmetric on blue line, symmetric on red line. And then you would get a measure at two antipodal points, north and south pole, measure of dimension 0. But on the boundary, you would get a Peano curve. Now, Oleg told us that this is not possible. But the optimal example should be close to this. So if this were possible, it would certainly be a dynamical systems object. Because some object where you, well, we have many holomorphic motions where you have Peano. For example, just take z square plus I and make 2 copies of this, and Jack Milner has a beautiful paper about it. So this is not possible. This is what Oleg ruined. But you know, what should please, to younger people, please prove constructive theorems. Don't ruin other people's dreams. But yeah, you should think what you want to prove before you prove it, and of the consequences. No, the Oleg is a very smart guy. It's a nice paper, and well, I mean, it was a sort of byproduct of something else. Now, so this is basically the thing that you take some dynamical object, holomorphic motion of it, that in the center you have a circle or a line or whatever, and you should have as many Peano curves on the boundary as you can. Well, probably it means that you can only have it 2 points, but again, you should have it as fat as possible elsewhere. So it's just, well, if you have some ideas, before the conference is over, tell me, and over Caipirinha. If not, like come to Geneva or somewhere. But this is indeed a thing where it might be. If someone comes with a nice example, there might be some canonical object behind it. So if someone comes with the example of canonical object, I will be very happy to sort of share it with you, or buy it from you, or steal.
Well, thank you so much, Stas, for that also philosophical advice to the new generations.
Well, Oleg was student of Kurt Macmillan, so it's Kurt Macmillan's fault that he didn't teach him not to ruin other people's dreams.
Okay, well, let's thank the speaker again.